The following assumptions should be met before doing a bivariate correlation analysis. So the first assumption is more of a methodological assumption and should be addressed both before and during the collection of data. The participants should only participate in the research once and have an influence, or not have an influence on the participation of others. The second assumption investigates normality. So each variable should be approximately normally distributed. The third assumption looks at the assumption of linearity. So there should be a linear relationship between the variables. If the relationship's not linear, then the Pearson's correlation coefficient will not adequately capture the relationship between those variables. And the fourth assumption looks at something called homoscedasticity. So homoscedasticity refers to the error variance being the same across the points of the linear relationship. In other words, the variability in one variable should not change considerably across the spectrum of the other variable.
So here we have our data for road rage incidents and the density of cars. So let's just have a look at this. We've got three variables. One is ID, cars, and road rage. Now if I go down to variable view here, we can see that I've got a bit more information on each of those three variables. So ID, that's just the identification, which is just used for general administrative purposes. Then we've got the variable cars. And you can see here that the label is the number of cars within 200 metres. So how many cars are within 200 metres of this particular car travelling on that section of the road. And then there's road rage, and that's the number of incidents of road rage while we're observing that particular car. So if I was to go back to our data view, and what we've got here is you can see that there are those three variables. So ID, cars, and road rage. So we can see here for participant 4. So participant 4, that has ID 4. There were 22 cars within that 200 metre zone that we were observing. So 22 cars around that particular, within 200 metres of that particular individual, participant 4. And road rage incidents are 6. So if you have a look down this sample here, you've got 44 particular individuals who are driving cars. And you can see that all of them displayed some form of road rage. So I've basically got a sample of people who are displaying road rage incidents. And I'm looking at the correlation here between cars and road rage. But what I want to firstly do here is I want to actually check for normality. So I simply go to Analyze, and then I go to Descriptive Statistics, and then Explore. Now what I'm going to do is I'm going to pull those two variables, number of cars within 200 metres and number of incidents. So I select those two variables and arrow them across to the dependent list. Then what I'm going to do is I can click on Statistics here, and I want my descriptives, but I won't worry about those three boxes here, so I'll leave the default descriptives on. What about plots? I'll click on Plots. And what I'm going to do is I'm going to choose dependents together. So I want to do box plots just to have a look for normality. So get a graphical representation of my data. And I'll get rid of my stem and leaf just to minimize the amounts of data that's coming your way. But what I do want to do is I want to tick normality plots with tests. So that'll generate my Shapiro-Wilk and Kolmogorov-Smirnov tests. And then I press Continue. Now if I look at options, I've got three options there. Missing cases listwise, exclude cases pairwise, report values. Let's leave it on the default of exclude cases listwise. And we're not going to go into the bootstrap options. And then if I press OK, what I'm going to do is generate the information.
The case processing summary table shows how many cases were analysed, how many were dropped due to missing data. So here we can see that there are 44 valid cases. The table of descriptives it contains a lot of information actually, including central tendency measures, range, skewness, and kurtosis. Now the skewness and kurtosis are measures of normality. Skewness, as the name suggests, indicates the extent to which the distribution is positively or negatively skewed. Kurtosis relates to how peaked, with thin or fat tails, is the distribution. So the more that these depart from zero, the less normal is the distribution. Now, dividing skewness and kurtosis values by the standard errors, which is in the last column of the table, gives you the Z-scores for both skewness and kurtosis. Now, since the Z-scores for both skewness and kurtosis are within the positive, negative 1.96 range for all the groups, this suggests that the two variables are approximately normally distributed on the dependent variable. Now, the Shapiro-Wilk is a standard test of normality. Both it and the Kolmogorov-Smirnov, which is a bit of a mouthful, but the Kolmogorov-Smirnov test tests the null hypothesis that the data are normally distributed. Now, they often lead to the same conclusion, but in the event that there's disagreement between these two types of tests, please choose the Shapiro-Wilk test of normality. Now, if the test is not significant, so in other words, if the p or the sig value is greater than 0.05, then the null hypothesis is retained and the normality assumption is met. The data are assumed to have come from a normal distribution. Now, if the test is significant, so in other words, the p or the sig value is less than 0.05, then the null hypothesis is rejected in favour of the alternative hypothesis and the normality assumption is not met. So the data are assumed to have not come from a normal population. So here the Shapiro-Wilk is 0.969 and the sig value is equal to 0.286 for the number of incidents of road rage variable and 0.963 with a sig value of 0.175 for the number of cars within 200 metre variable. And this suggests that normality assumption is not violated. Now, histograms and stem and leaf plots and box plots can also give you a good idea of what the data looks like in a visual perspective. So here I show you the box plots, also called box and whisker plots, which can be useful because they also provide a good representation of the distributions and also help you to identify any potential outliers. So the box contains the middle 50% of scores, so from the 25th to the 75th quartile of scores. The line in the middle of the box represents the median of the distribution, while the whiskers that you can see extend to the highest and lowest points in the distribution that are not outliers or extreme scores. So here you can see that each box plot which is done for each variable is roughly symmetrical, which further confirms that each group is approximately normally distributed. Outliers and extreme scores are also shown in box plots. Here you can see that there aren't any. If you wanted to confirm any suspected outliers, you can obtain a Z-score of the participant's score, and any participant with a Z-score of more than 3.29 is an outlier. Now, I've not conducted Z-scores in this analysis as it's not necessary. Now, if there were outliers in this distribution, each would be denoted with a circle and a data file or data file row number. On a box plot, an outlier is defined as a score between 1.5 and 3 box lengths above or below the box boundaries. If there were extreme scores, each would be denoted with an asterisk and a data file row number. So on a box plot, an extreme score is defined as a score of more than 3 box lengths above or below the box boundaries.
So one way to look at your data, number of accidents or number of incidents of road rage and number of cars on the road. So one way to look at that data is to do a scatter plot. And a scatter plot's a good way to see whether your data is homoscedastic or heteroscedastic. So to do that, we go to graphs and then we look at legacy dialogues. Now I wanted to do a scatter plot. So what I'm going to do is I've got a few choices here, but what I'll do is I'll just go to scatter. And what I'm going to do is choose a simple scatter plot. So I'll just simply choose simple scatter plot and define. Now you've got a couple of choices here about what variable you want to go into y-axis or into x-axis. So the variables are the number of cars within 200 meters, that one, or the number of incidents of road rage. Now in this example, we're using the number of cars within 200 meters to predict the number of incidents in road rage. So we have a hypothesis that the more cars there are on the road, probably the higher the incidence of road rage. Now, given that's the case, so given that we're using a number of cars within 200 metres to predict the number of incidents of road rage, well, then what that means is by convention, the predictor always goes on the x-axis. Now, in our case, the predictor is the number of cars within 200 metres. So we're using that as our predictor of number of incidents of road rage. And the criterion variable is, or our otherwise known as our dependent variable, goes into our number of incidents of road rage. Now, what I can do here, you can click on titles and you can choose the titles that you want for particular lines. Or you can click on options here, and I'm just going to leave it all as the default. And what I'll do is I'll press OK.
A quick visual inspection of the scatter plot confirms that the relationship between the two variables is linear. That is, that they're roughly a straight line. The assumption of linearity has not been violated. So in addition, there appears to be roughly the same amount of variability in the number of incidents of road rage at all levels of number of cars within 200 metres. So this also suggests that the relationship between the two variables is homoscedastic. So if these assumptions are violated, then consider using the Spearman's row. A heteroscedastic relationship may look closer to this. A heteroscedastic relationship is where you might observe low levels of car density on the left of the graph, and there's also very little variability in road rage data. However, as the scores on density increase, so too does the variability in the road rage.
Now we're going to conduct a bivariate correlation. So to do that, we go to Analyze, and then we go to Correlate. And then you'll see that there are a couple of options there. Let's choose Correlate and then Bivariate. Now, the two variables that we want to correlate are number of cars within 200 metres and number of incidents. So let's pull those over to the variables there. And you can see that there are a couple of other options that we can choose here. So let's just click on the options here. So we can click a number of statistics there. I'm just going to leave it as the default. I'm not going to worry about the bootstrap. Now, under the correlation coefficient, select the Pearson. We're doing a Pearson correlation coefficient, and this is the default in SPSS. And also two-tailed as a test of significance. This is also the default. And despite some debate, there does appear to be relatively few instances where we would choose a one-tailed when we're looking at a Pearson correlation. So we leave it ticked as two-tailed. And then what we're going to do is we're going to press OK.
A Pearson correlation statistic can be either positive or negative, and it can range from +1 through to 0 through to -1. With 0 indicating the absence of correlation. Now, when you do a correlation analysis, the correlation table has 3 rows. The first row reports the correlation. The second row reports the significance, the two-tailed significance levels, which is also the p-value. And the third row gives us a number of participants in the sample. So in this example, the Pearson correlation between the number of cars within 200 metres and road rage incidents is 0.973. So this is a very high positive correlation. And when you look at the second row, you can see that this correlation has a significant value of 0.000, which is significant. It's below the alpha level of 0.05. And since the relationship is positive, it indicates that the variables covary in the same direction. Low numbers of cars on the road tend to accompany low levels of road rage incidents, while high numbers of cars on the road indicates or tends to accompany high levels of or high numbers of road rage incidents. So please look at your text to see how to write up a correlational type analysis in APA format.